3A, measures of center. Okay, so now we're going to talk about the centers of data. And we have three main measures that we use for measure of center: mean, median, and mode. We're going to talk about those, and then we're going to talk about some variations on those, you could say. So let's start out with a number of data points. 36, 42, 51, 36, 29, 48, 73, 41, 39. So now I have a number of data points. How many do I have? Just to count: 1, 2, 3, 4, 5, 6, 7, 8, 9. So n is equal to 9. So we're going to talk about these measures of centers. The first one we're going to bring up is the mean. You're already familiar with the mean. You probably just didn't call it that. That's just what we call an average. The mean is just the average of the data points. And we have to kind of separate it into two pieces at this point because we have a population mean and we have a sample mean. They're calculated the same way, but we use different variables to define them. So if I make this the population mean, the population mean is defined by the variable mu. That's the Greek letter mu, mu, and that's used for a population mean. It's found by summing up the data points, so the sum of x, where x is any particular data value, and dividing by the actually the population size, which is capital N. So I'm just going to put that down for a population size, capital N. So that means to find our population mean of this data, we would add up all these data values, and I'm just going to grab a calculator here. So we would just add all these up. So 36, 42, 51, 36, 29, 48, 73, 41, 39. We're just going to add those up. So we get 395. And then we're going to divide that by n, the population size. So that's 9. Which gives us 43.8 repeating. So our population mean, mu, is the sum of x over capital N, 395 divided by 9, or 43.8 repeating. So that's the population mean. Assuming this was a sample, which is actually what it was, things don't change a lot. The sample mean is x bar. Now, in statistics, generally, we use Greek variables for population parameters, and we use Roman letters, our standard alphabet, for sample statistics. So, sample mean is x bar. It's found the same way. I'm just going to get this population size out of here so it doesn't get in our way. So we just sum up our data values and divide by lowercase n the sample size. So using the same numbers, we would end up with 395 divided by 9, or 43.8 repeating. So the calculation is done the exact same way. It's just a matter of, are we dealing with a population or are we dealing with a sample? Now, as I said, the mean is a very common method for us to use to find a center. You've dealt with it before. It's just what we consider an average. But the mean has a problem. I'm going to introduce you to a term, resistant. I'm just going to put it over here. The term resistant. Now, when we're talking about a statistic or a parameter, we say it is resistant if extreme values, or values that are far away from everything else, do not have a large effect on that parameter or statistic. Now, the mean, unfortunately, is not very resistant. Meaning that if we have an extreme value, it could change this quite a bit. If our largest value was 1,000,000 instead of 73, then our average would skyrocket. So it would have a huge effect on it. So the mean of a set of data can be greatly affected by an extreme value in the data. And that's why many times you'll hear people use another measure of center, which is the median. The median, it doesn't matter whether we are dealing with a population or a sample, it just means the middle. It's the middle data value, meaning if we put our data into order from least to greatest, it will be the middle value. So looking at what we have right here, I'm just going to go from smallest to largest. Looks like our smallest is 29, followed by 36, 36, 39, 41, 42, 48, 51, 73. Now, when we're reordering these to find the median, it's always a good idea to take a moment and do a little sanity check and make sure we still have all the data values. 1, 2, 3, 4, 5, 6, 7, 8, 9. I still have 9 data values, so I got all of them, and now I have them in numerical order. So I'm just going to look for the middle data value. 1, 2, 3, 4, 5. So there we go. So the median of this set of data is 41. So if we have an odd number of data values, once we put them in order, the middle data value will be your median. If you have an even number of data values, then you will average the middle two numbers. So if we had, in addition to these numbers, let's say 27 was also a data value. Well, now we have 10 data values, so the middle two data values would be averaged together and we would get 40, and that would be our median. So if we have an odd number of data values, once they're put in numerical order, the middle data value is your median. If you have an even number of data values, once they're put in order, you average the middle two values, and that gives you your median. Now the median, as you can see, actually is very resistant. If this number, instead of being a 73, was 1,000,000, that would have no effect on this median value, because it's the middle values that make a difference. And you see this a lot. You hear people talk about median income, median home prices, median cost of living, or whatever the case may be. And that's why they do it, because the extremes don't have as much effect on it. So that's our second measure of center. Our third measure of center is mode. And mode can be interpreted as most. It's the value that occurs the most. So if you look at your data values, and it's really easy if we look at them once we've got them put in order, we see that 36 occurs more than any other value. Every other value occurs once, 36 occurs twice. So our mode would be 36. So it's the data value that occurs the most. And in this case, since there was one mode, we would call this unimodal, meaning there is one mode. If two data values occurred the same amount of times, such as if there was another 48, now we could say that it was bimodal because the mode would be 36 and 48. If we had another duplicate, say another 29, then it would be trimodal, where 36, 48, and 29 are modes. If we had four data values that repeat, that's when we start to call it absurdimodal, because we just don't really deal with more than trimodal. When you get to the point that there's more than that for peaks or highest frequencies, it really stops telling us much of anything. But the other thing that's important for us to note is sometimes there is no duplication. So what if there was only 136 there? Now everything occurs the same amount of times, and we would say there is no mode. Do not say that the mode is 0, saying that there are no modes to it, because that would actually tell us that the mode was 0. So no mode, or sometimes people just say NA for not applicable. So let me put my 36 back in here again. We have our mean, which could be a population mean, mu, or a sample mean, x bar, calculated by summing up all the data values and then dividing by either the population size or the sample size, respectively. Our median, found by putting all our numbers in numerical order, and then just finding the middle data value after doing that. And our mode, which we can put back to 36 now, that 36 is back here. So our mode is the value that occurs the most. And there may be 2 or 3 values that are modes, or you may have no mode. And there we have our 3 measures of center that we deal with regularly. Now the mode also is resistant. Because if you think about it, what does it take to change the mode? Well, the mode is what occurs the most. So to change the mode to something else, that something else has to occur the most times. By common sense, we can see that if something occurs the most times, it's the most frequent thing to occur, that's not an extreme data value, that's a data value. It's what's occurring the most. So median and mode, very resistant, mean, not resistant. Keep those in mind. Another thing that we may deal with, and I took that out of the way so I can put something in place of it, outlier. An outlier, that's just a term that states that something is far away from everything else. So in this case, we look at this and I go, gee, in this data, possibly 73 is an outlier. Notice how other things are a little closer together, and then that jumps over 20 to get there. This one was only a difference of 7. Difference of 7, 0, 3, 2, 1, 5, 6, 3, 22. That's a huge difference. So that could potentially be an outlier. At this point in time, the best we can do is give a subjective answer to whether something's an outlier and say, yeah, that seems like it's far away from the rest of the data values. Therefore, it's probably an outlier. In a couple sections, we'll get to the point where we'll talk about how to determine if a value is an outlier and how to work with that. Okay, so those are our basics for measures of center. So now we're going to go to some slight modifications of this. and we're going to look at a frequency distribution mean. Now, frequency distribution means are pretty cool because when you set up a frequency distribution, sometimes you're set up like that because that's the way the survey went. You sent out a survey and it asked for ages, and it gave you from 10 to 19, 20 to 29, 30 to 39, 40 to 49, 50 to 59, right? And then you get the data back and you know that however many people said they were in this age bracket and how many in that age bracket. And then you go, gee, I'd really like to know the average age of the person who responded to the survey. Well, that could be a little difficult at that point, couldn't it? Because we didn't ask them their ages, we asked them an age group. Let's try a little experiment. I'm going to set up a bunch of ages up here, people responding to the survey, and I'm going to create a frequency distribution from that using, I'm going to assume that everybody's over 20 responding to the survey. Just because we're going to work with adults here. So let's get some ages here. So we got someone who's 29, 56, 71, 49, 42, 37, 35, 21, 24, 38, 40, 63. Okay, so we've got a bunch of people, and let's say we asked them the question, so we had the ages, and we went from 20 to 29, 30 to 39, 40 to 49, 50 to 59, 60 to 69, and we went up to 70, so 70 through 79. And so we're going to create this frequency distribution from 20 to 29. We had 1, 2, 3 people in that age group, 30 through 39, 1, 2, 3, 40 to 49, 1, 2, 3, becoming common here, 50 to 51, 1, looks like just 1 there, 60 to 69, 1, 70 to 79, 1, and again we do that sanity check. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We sampled 12 individuals. Then we got 9, 10, 11, 12. Okay, so we have everybody that we want. So now we have this frequency distribution. Now remember, we did a survey and they filled in this information. We don't have those original data values. But I'm just going to do a quick check here. I'm going to see what the average age of the respondents actually is. So again, I'm just going to do the standard find a mean. So I'm going to add them up. 29, 56, 71, 49, 42, 37, 35, 21, 24, 38, 40, 63, which gives us 505, and then we're going to divide that by 12. So we got 42.083 repeating. So x bar is equal to 42.083 repeating. So we're just going to put that there for future reference. So now, what I'm going to do here is I'm going to take this frequency distribution. Remember, we don't have that data. Those are the ages of the people who responded, but this is what they told us. They just told us which age group they were in. So how can I average these out? What we're going to do is we're going to use the midpoint. Excuse me. The midpoint, just like we did for some of our graphing of frequency distributions. So we're going to take 20 plus 29 is 49, divided by 2 is 24.5. And then, since 30 minus 20 is 10, we have a class width of 10, so I can just make this 34.5, 44.5, 54.5, 64.5, 74.5. So now I have my midpoints. I'm going to treat those midpoints as x, as if they were data values. The midpoint's my best guess for each of these values that we're representing. So 20 to 29, we're assuming that the midpoint's going to be our best guess. Because you think about it, it can only be 4.5 off either direction. If I were to choose 20 as my representation, I could be as far as 9 off. If I chose 28, then I could be as far as 8 off, right? So choosing the ends is bad, whereas the middle, I minimize how far off I could really be from the real data values. So I'm just going to use that, and I have to realize that I have 3 of these 24.5. So what I'm going to do is I'm going to take f times x. I'm going to multiply this 3 times 24.5. So 3 times 24.5 gives me 73.5. Then I'm going to take 3 times 34.5, which gives me 103.5. 3 times 44.5, 133.5. 1 times 54.5, obviously 54.5. 1 times 64.5, 64.5. And 1 times 74.5, 74.5. Well, now that I have these, this is essentially me adding up all of the ages, our estimated ages from the first group. We had 3 at set 24.5, so we came up with 73.5. Adding up all those, adding up all these, adding up all those. So if I add this up, I get 504. And that's the same as me summing up all the data values. Now, if I remember correctly, that's pretty darn close to what we came up with for the actual sums. But now we're going to divide by the number of data values, 12. $504 divided by 12 gives me an average age of 42. The actual average age was 42.083. We're off by less than a tenth for the age. That's incredible. Now I'll tell you, it doesn't always work out that well. But it does get you really close to where you want to be. In reality, it can only be the maximum error we could have in finding this average is 4.5 in this case, because that was our distance from the midpoint to a class limit. So the maximum error we could have would be if everything was all the way to the lower class limit or all the way to the upper class limit. So you're one half of your, not even your class width, but 1/2 of this difference is the most you could be off. And we came off by less than 0.1. Now, there officially is a formula for this, and you say that the frequency distribution mean is equal to the sum of f times x over n. Now remember, this symbol means summation. That's just addition, which means you multiply f times x, then you add them up, and then you divide by n. We multiplied f times x, then we added them up, and we divided by n. And that's how we get a frequency distribution mean. I think it's pretty cool. You can take a distribution of data and not know what the original values are, and you can get a pretty good approximation of what the mean of the original data was. Frequency distribution mean. Another mean that should be very important to you is a weighted mean. I'm going to get these out of here too, I don't need those. A weighted mean is where you have a bunch of data values, but each of them is worth a different amount when doing the calculation. What we've dealt with thus far treats every data value as if it's worth the same thing. Whereas now, we're going to look at, well, what if this one is worth more than that one towards the final average? A great example for a weighted mean is a class average. Because that's really what a class average is. Take this class, for example. So we have participation, we have homework, we have exams, and a final exam. Participation is worth 10% of the class grade, homework's worth 20%, exams worth 50%, and the final worth 20%. What that says is, your participation in this class is worth half as much as the final exam. All these homeworks that you do during the semester are worth the same amount as that one final exam. Your 4 final exams in this class are worth a combined total of 50 points, whereas the final exam itself is worth 20 points. So 50 divided by 4 is 12.5. So each exam in this class is worth about 12.5% of the class grade. Your final exam is worth almost double that. It's worth 20% of the class grade. Now, of course, we know that there are a number of things involved with this. For instance, participation, that's pretty straightforward. You have one participation grade. But homeworks, you're doing a number of homework assignments, and all of them add up to a total of 20% of your class grade. So if you do 20 homework assignments, that means each homework assignment means 1 point on your final grade. Whereas the final exam is worth 20 points, 20 times as much as that. Exams, we know we've got 4 of them to get that total of 50. So let's do an example here. I'm not going to use as many grades as we possibly could in that, but I'm going to say, what if you have a participation grade of 98? On your homeworks, you got a 95 and a 97. On your exams, you got a 78, an 83, and 79. And then on the final exam, you got 75. So let's look at this and see what we can find for our weighted mean. Well, the first thing we're going to do with that is we're going to average each of these categories. 98. So the average of 98 is 98, nothing to average it to, right? 95 and 97, add them up and divide by 2 gives us 96. 78, 79, and 83. 78, 79, 83. Gives you 80. 75 averaged is 70. So what we're going to do now is, now that we've got those averaged, we're going to call that x. We're going to take these and go, okay, The average with that is that, so this 98 is worth 10% of the class grade. This 96 is worth 20%. This 80 is worth 50%, and this 70, let's try 75 like it's supposed to be. This 75 is worth 20%. And this just shows how easy it is to accidentally write a wrong number down and have everything thrown off. So now that we have that, I'm going to find the weight. And there are a couple ways that people do this. I like to find the weight initially, use this, find the weight, and then multiply by it. Other people will just solve everything and then they'll divide by the weight, or the total weights, I should say. So I like to do it this way. So first of all, I add all this up, 10, 20, 50, 20, gives me 100. So my weight, WT for weight, is 10 divided by 100, or 0.1. 20 divided by 100, 0.2. 50 divided by 100, 0.5. 20 divided by 100, 0.2, which obviously when we add those up gives you a total of 1. And this is why I like to do my weights this way, because it makes it nice and easy. Because my next step is I'm going to multiply each of these values times the weight. So 98 times 0.1 is 9.8. 96 times 0.2, 19.2. 80 times 0.5, 40. 75 times 0.2, 15. And if I add those up, I'll have my grade in the class. So you have 9.8 times plus 19.2 gives me 29, plus 40 gives me 69, plus 15 gives me 84. So what is the class grade? It's an 84, and that's the weighted mean. We took all of our categories and we averaged each of them to get a single number that represents those values. We then found our weights, which was we took the proportions here, whatever they're worth, and put it over that. The weights are kind of like relative frequency, aren't they? 10 out of 100, 20 out of 100. So we could have this on a point system that doesn't even come out to be 100. It's just this over the total amount, this over the total amount. Then we multiply our value that we got times the weight, sum them up, and that gives us our average in the class, or our weighted mean. Now, just for the fun of it, I want to look at what if all these grades were worth the same. If there wasn't a weighted mean, if it was just a standard mean. We have 98, 95, 97, 78, 83, 79, 75, which gives us 1,486 divided by, what are there, 7 of them? And that would be very wrong. I typed something in wrong. 98, 95, 97, 78, 83, 79, 75. And I add them up and I get a much healthier 604 divided by 7 would give us an 86.43. So we can see that these grades, our grade in the class would have been higher if each of these things was worth the same thing. So what pulled it down? Well, the fact that 70% of the class grade was dealing with these values that were less than 90, only 30% were above 90, so this helped to pull it down. Notice that all of these are below the actual weighted mean. So it had more of an effect on it. Now I want to do a little side note with this and say, well, Mr. Davis always makes a claim. I claim that if students do what I ask of them, that they will pass the class. I have never had a student do everything that I've asked of them who has not passed the class. And I'm not saying because my students are all brilliant or that I make them do all sorts of ridiculous things, just sticking to the basic things that I require of my students. And I'm going to show you how this works. Participation. If you watch all the lectures and do all the work, then you get 100 for participation. And I'm actually going to simplify this a little bit rather than, I'm just going to move it over here and say, okay, well, assuming that you do this for all the things, if you hand in your homework assignments on time, you get a 100 for your homeworks. Okay, so you take the exams, you're not a great exam taker. Let's say you get a 59 average on your exams. So you essentially have a failing exam average, 59. And on the final exam, you get a 59. Remember, you don't have to pass the final exam to pass the class. You have to take the final exam to pass the class. Now, obviously, if you're doing all your homeworks and you're participating in the classes, then your exam grades are going to tend to do better than if you're not doing homework. Right? So let's work on this assumption here. Well, we still have the weights of 0.1, 0.2, 0.5, and 0.2. So 100 times 0.1 is 10. 100 times 0.2 is 20. 59 times 0.5 is 24.5. Sorry, 29.5. And 59 times 0.2 is, what, 111? Just say. Sorry, 11.8. So 11.8. And if we add those up, what do we get? 10 plus 20 is 30, plus 19.5, sorry, 29.5, so 30, 59.5, plus 11, 69, 70.5, 0.8, 71.3. So if students do everything I ask, just in participating and attending all classes, doing all the homework assignments on time, and then taking the exams, and like I said, if you study and you prepare and you're actually doing the homeworks instead of just throwing random things down, you're going to do better on the exams. You could essentially have a failing exam average and still get a C in the class. So where would your exam average have to be to get it down to an F in the class? You'd have to drop 12 points off of there. So your exams would you'd have to have exams in the 40s. All of your exams would have to be in the 40s for you to fail the class if you do everything else right. Or somewhere around there, 50 or below. So, can you pass the class? Of course you can. Are you willing to pass the class? Well, that's a different question. So there we go, that's weighted mean. Okay, so last thing I want to talk about with measures of centers, I want to talk about shapes of distributions. And what do I mean by shapes of distributions? Well, I mean just what I said. There are 4 shapes of distributions that I want to talk about. The first we call symmetric. And a symmetric distribution, okay, you got this middle line here down here, that is the mean, the median, and the mode. Now in a symmetric distribution, that means if I take this dotted line, I fold this graph over at that point, that it'll fit exactly on top of itself. It mirrors over that middle point, which is the mean, the median, the mode. So that's a symmetric distribution because it's the same on both sides. Now here we see something that kind of looks like the symmetric distribution, but it seems to have veered off to the side here. This is what we call left skewed. Or skewed left. Some people say skewed left, other people say left skewed. But left skewed, this peak, if we think of this as a frequency histogram, that's the highest frequency, that's the mode. So the highest point on our distribution is always going to be the mode. And then you can see that this trails off to the left-hand side, thus the left skew, right? And what that does is, since that's trailing off to the left-hand side, it moves the median a little bit to the left of the mode. And then this trailing here, remember that the mean is not resistant. So that causes the mean to get even pulled further to the left. So that's a left skewed distribution. Obviously, if we have a left skewed, we must have a right skewed. Or skewed right, depending on how you want to say it. And it does the exact opposite of left skewed. The highest point, of course, is the mode, but then the median gets pulled a little to the right, and the mean gets pulled even further to the right. So we've got our mode, our median, and our mean. And then the final one is uniform. In a uniform distribution, you can see it's all the same. The center point here is the mean and the median, but there is no mode. Because each value occurs the same amount of times. So that's a uniform distribution. Well, why do we care about that? What does that do for us? Well, if we understand how these work, we can look at the mean, the median, and the mode and estimate the shape of the distribution. So let's do that. I'm going to give us mean, median, and mode, and we're going to determine what shape it is. Unfortunately, I've got to get these off the board because they're too big and they're in my way. Okay. We have a mean of 76, a median of 76, and a mode not applicable. So no mode. So if we have a mean and median and they're the same and we don't have a mode, then our estimate is that this is a uniform distribution. What if the mode was also 76? Well, if that's the case, then we have a symmetric distribution. Mean is 45, median is 48, mode is 50. Okay, so mean is 45, median is 48, mode is 50. That would be left skewed. Left skewed. How do I know that? Well, if I put these on a number line, we got 45, 48, 50, right? We know we have the mode is going to be the highest point on this, so it's curving down somewhere around there. And then we come over to the median and the mean, and we've got this drag off to the left-hand side. Well, you may say, Mr. Davis, that may be obvious to you, but that's not necessarily obvious to the rest of us. And that's okay, because I'm going to teach you a little trick, which is going to allow you to get this right every single time. All you have to do to determine whether you have a left skewed distribution or a right skewed distribution is list the numbers in numerical order, 45, 48, 50. You don't even have to space them out correctly. Just list them in order. Go to your mode, find out which one that is. That's going to be your highest point on your graph. So put a line there saying, hey, this is my highest point. And then start from that side, come up, and sweep across. What do we have? Left skewed. It's skewed to the left. "96, 94, 91. Well, we know it's not symmetric, we know it's not uniform, so we put it in numerical order, 91, 94, 96. The mode is 91. We come up and swing across, skewed right. Works every single time. And that's dealing with measures of center.